Welcome. Today we are driving into a machine learning project aimed at revolutioning the abalone farming industry. Traditionally, determining the age of an abalone, a critical factor for sustainable harvesting, requires manually counting growth rings on its shell, a laborious and time-consuming process. By leveraging physical measurements like length, diameter, and weight, this project automates age prediction using machine learning. Over the next 10 minutes, I will walk you through the key processing steps, explain why models like random forests and decision tree are ideal for this task, and reflect on the real-world implication of the results. Along the way, I would tie in core concepts like the bias-variance trade-off and validation strategies to illustrate their practical importance. Let's get started. So let's first talk about the data processing. The dataset used in this project contains 4,177 abalone samples, each described by features such as sex, length, diameter, and several weight measurements. The target variables is the number of rings in the shell, which directly correlates with the age, and the formula for the age is age equals rings plus 1.5. Before training any models, the data underwent critical processing steps to ensure robustness and accuracy. First, outliers in the target variable were addressed using the turkey rule, which identifies extreme values based on the interpretile range, IQR. For instance, abalones with unusually high ring counts were rel and risk screwing predictions. Removing these outliers reduced noise as visualized in a box plot of the rings distribution before and after processing. Next, categorical features like sex categories. There are like some examples of categories like male, female, infant were converted into numerical values using label encoding. While simple, this method assumes an ordinal relationship between categories, a potential limitation as biological sex doesn't follow a natural order. Future irritations might benefit from one-hot encoding to avoid this assumption. Finally, feature scaling was applied using standard scaler to standardize the range of numerical features like weight and diameter. This step is crucial for models like support factor regression and k-nearest neighbors, which rely on distance metrics. Importantly, scaling was performed after splitting the data into training and test sets to prevent data leakage, ensuring the model's evaluation remained unbiased. EDA further guided processing. Tools like AutoVis revealed strong correlations between weight-related features like whole weight and shell weight, suggesting potential redundancy. Additionally, features like height exhibit right-screwed distributions, hinting that log transformations might improve model performance, so this wasn't explored in the current workflow. Now let's talk about the modeling and the validation. With pre-processed data in hand, the project tests several regression models, including linear models, multiple linear regression, lasso, ridge, tree-based algorithms, decision trees, random forest, and nonlinear models like SVR. Each model's suitability was evaluated based on its ability to balance bias, underfitting, and variance overfitting, a core concept in machine learning. Random forest was an earlier standout. Beyond its predictive capabilities, it provided feature importance scores, revealing that shell weight, diameter, and length were the strongest predictor of age. This aligned with biological intuition. Larger, heavier oblongs are typically older. However, while random forests handle non-linear relationships well, its ensemble approach introduces complexity that might deter stakeholders seeking simplicity. Decision tree, on the other hand, achieved competitive results like MSE equals 4.64 and R square equals to 0.56 by directly modeling nonlinear patterns in the data. But their tendency to overfit, evident in the gap between training and test performance, highlight the bias-variance trade-off. A deeper tree might capture more nonsense, but risk memorizing noise, whereas a shallower tree might oversimplify the problem. In contrast, linear model like multiple linear regression struggled. MSE equals 6.11 and R square equals 0.49, reflecting their higher bias. These models assume a linear relationship between features and rings, which fails to capture the complexity of biological growth. Regularized variance. Lasso Ridge improved slightly but couldn't overcome this fundamental limitation. The validation strategy relied on a 80-20 train test split, a programmatic choice for initial testing. However, more robust methods like k-folder cross-validation would better estimate generalization error, especially for the model sensitive to hyperparameters like SVR. For example, SVR's polynomial canal achieved moderate results, MSE equals 5.20. But a grid research could optimize its parameters and improve performance. And let's talk about the insights and real-world implications. The results of this project carry significant implications for both industry practices and machine learning workflows. The decision tree model R-square of 0.56 indicates moderate success, but the maximum error of 72% in extreme cases underscores a critical challenge. Predicting the age of rare, very old oblongs, this suggests the need for stratified sampling or oversampling techniques to balance the datasets and improve performance on underrepresented groups. From a business perspective, even a partial accurate model could transform the industry. Automating age estimation could save hundreds of labor hours annually. Imagine processing 100 oblongs in minutes rather than days. This efficiency gain directly translates to cost savings and scalability, enabling farmers to meet growing market demands. Sustainability is another key takeaway. Accurate age prediction ensures oblongs are harvested only after reaching maturity, aligning with regulatory standards and ecological preservation goals. However, stakeholders might resist adopting black box model like random forest. To address this, tools like SHAP values could provide interpretable explanation for the predictions, building trust among farmers and regulators. Finally, the project highlights the importance of validation and bias variance trade-offs in real-world applications. While linear models underfit and complex tree overfit, a well-turned insensible method like gradient boosting could strike a balance. offering both accuracy and reliability. And in summary, this project demonstrates the potential of machine learning to streamline Avalon age prediction while emphasizing the importance of rigorous pre-processing, model selection, and validation. The key recommendations moving forward are threefold. The first is model improvement. Explore advanced ensemble methods like charge boost or light GBM, which often outperform individual models. Hyperparameter tuning, like adjusting tree depths or regularization terms, could further refine performance. The second, data enhancement. Address class imbalance through techniques like SMOT or targeted data collection for rare old Avalons. The third one is stakeholder collaboration. Work closely with farmers and regulators to design user-friendly tools, like a mobile app or API, that provides actionable insights while maintaining transparency. By bridging the gap between technical experimentation and real-world application, this project not only advances sustainable aquaculture but also serves as a blueprint for solving similar challenges in agriculture and conservation. Thank you for joining me on this deep dive. Let's continue to innovate for a better future. Thank you.